Okay, today we are here for the final presentation on the Ariadna project, the Space Gaits. And this project has been initiated by the Advanced Concepts team of the European Space Agency. So the involved people were me and Dario. And then, as all Ariadnas, we work together with university. In this case, it was the National Technical University of Athens, the Control Systems Laboratory. And Evangelos Papadopoulos, Joseph Paraskevas, Ioannis Kontolatis, and Dimitrios Miliciotis. I don't want to take away too much of the content that Evangelos will present in a second, but I would like to present the main idea that we had behind this study. So currently, as you know, space exploration is done with, on planets like Mars, is done with rovers that have wheels, but often with these rovers, the scientists cannot get at the really interesting places for them. So there would be a real opportunity by using walking robots. But at the moment the research on walking robots is progressing, but it's still not there yet. And in this study we thought, okay, most of the walking robots are tuned to a specific environment, so normally Earth. But there are a few studies that look at, for example, Mars. And what we thought was lacking was a general approach to design and select appropriate walking gaits for different space environments. So this can be, of course, gravity is an important one. And so if you think of the astronauts walking on the moon, they were like hopping like rabbits or something. Also because it was a nice way for them to walk and perhaps energy efficient. But the question is, okay, when should you walk in what way to optimize things like energy efficiency or speed or things like that. So we wanted, we came with an approach to this, and then we sat together with the National Technical University of Athens, and they actually did a lot of work on this.
So, good morning, ladies and gentlemen. I'm going to report on our Ariadna study called Space Gaits. This is the executive summary, and this is work done at the Control Systems Lab, Department of Mechanical Engineering at the National Technical University of Athens. The motivation for this work is we have celestial bodies which need to be explored, and the surface there is quite hard. We have a highly unstructured terrain, and the morphology of the terrain changes within few meters. However, the scientists have interest in these areas, which are very hard to reach. And so in those cases, legged robots can be a solution. Good things about the legged robots are that they can handle discontinuous terrain. They can decouple the body motion from the leg motion, so that you may go over uneven terrain, but your base can remain level. And also they have a small and discrete footprint, and you don't get a lot of disturbances due to wheels and wheel interactions. So here we see a Mars picture, and this is a robot that we have constructed, built in our lab. So the problem statement is that in legged robotics you can find a lot of work which is related to the various designs that you can have, the models that describe them, and the control algorithms which run on them. But and most of them are proposed for the Earth. There is no work for other planets, and what is missing though is a strategy and methodology for classifying the gaits that robots undergo, and there is a need for selecting the optimal gaits, which are the best gaits in terms of various indices, and with respect to the environment and the mission constraints. The roadmap for this, the Space Gaits resources, the people who worked at NTUA besides myself is Mr. Ioannis Kontolatis and Joseph Paraskevas, who are PhD candidates, and we got also help from Dimitrios Miliciotis, an undergraduate student, and people at ESA, Dr. Guido De Crom, and Dr. Dario Itso, and we collaborated using a wiki, a special wiki, email and Skype communications. The time frame, the project started in May 2012 and essentially ends today. So this is the roadmap of our work. I'll talk first a bit about the quadruped robot that we use in our work. I will present the environmental conditions that this robot had to face. I'll explain how we did the gate classification and how we choose optimal gates, and show some results and conclude this short presentation. So this is the quadruped model. It's a base with mass and inertia. There are legs. There are 4 legs, but the legs move in pairs. So we have the virtual leg, which means that there is a single leg, but with twice the stiffness and damping, which is in here. And the leg can have mass and inertia. The robot is moving on an incline in general at an angle of 5. We have actuated hip joints here and there. There are 4 motors, and there are 4 passive prismatic joints, which are the linear springs. So the body can rotate around the z-axis, which is here, and this is the pitch angle, and the pitch rate, of course, follows. And this system is highly under-actuated, because if you count all the degrees of freedom, you have much less motors, and this is done to save energy, basically. If you can do it with less motors, it's better for you in terms of efficiency. Now, this robot undergoes some phases, and you can have two different gates, the pronking and the bounding. In the pronking, you go from flight, where all legs and the body is up in the air, to a double stance, where the 2 legs hit the ground. And so this is pronking. But you can have intermediate phases, where one of the sets of legs is at stance, like going from flight to rear stance, double stance and front stance, and then back to flight. So if this keeps on, you get gaits and repeated motion and repeated displacement. The triggering event is the leg length comparison, so we check what is this distance basically, and if this becomes 0, then the leg hits the ground. And because each phase has its own dynamics, this system is hybrid. So there are different dynamic models that correspond to each of these 4 or 2 stances. So this is a quite difficult system. It's under-actuated and it's hybrid at the same time.